This is a section on turboprop and turboshaft controls. There are basically two types of turboprop and turboshaft engines. They're either the fixed shaft turbines or they are a free turbine. First, we'll take a look at a fixed shaft turbine. This is a cutaway of a TPE 331, and we have a cutaway in the classroom. It's got a tire bolted onto it instead of a propeller, and it's got a main shaft running through the engine. Drives 2 stages of compressors, drives 3 stages of turbines, and this shaft goes into the propeller reduction gearbox. And there it goes slower. In this case, the engine spins at 40,000 RPM, and the propeller spins at 2,000 RPM. And of course, that's why we have the gear reduction. And it's always connected. If you come up to this propeller and start spinning it, the engine will spin. And if you go over to our cutaway, you'll find when you spin the tire, the engine spins. That's why it's called a fixed shaft engine, because the turbine is always fixed or attached to the output shaft, whether it's a propeller or an output shaft for a transmission on a helicopter. It doesn't make any difference. One nice advantage of that kind of an engine is that you only have 1 RPM to control. So you only have 1 RPM gauge. You only have to make sure that one rotating component has a controlled RPM. If you looked at this turboprop, in fact, our stick diagrams that we've been drawing of turboprops are of the fixed shaft type. The shaft comes out, we've got a gear reduction box, and then there's a propeller, and if we spun the propeller, the engine would rotate. And since it does rotate, since the engine and the propeller spin together, if we put an accessory gearbox on this engine and then had a starter motor, actually somebody's going to do that. Not only is it going to have to spin the engine, but it's going to have to spin the propeller. So in that case, since it's going to have to spin the propeller, that propeller is going to be held in low pitch when the engine shuts down, so that when the starter has to spin the engine and it has to spin the propeller doesn't have too much drag. So it's got the blade latches in there that grab the blades when the propeller shuts down, just like in a Seminole, so that the blades are held in low pitch when the engine shuts down. A free turbine, on the other hand, if you were going to draw a stick diagram of a free turbine, there's more than one way to do it. Let's see. Here's one way to do it. Whoops, it's a pretty lousy propeller. You could run like that. You could have a 2-spool engine that looked like this, and this one turbine that drives the output shaft and the gearbox going to the propeller, it gets a spin at 1 lower RPM, typically, although you're still going to have a propeller reduction gearbox. And then the rest of the engine here, that's going to be N1. This RPM they're probably going to call the propeller, although you could call it N2. This is probably going to spin faster. And this turbine that is spinning the propeller is free from the rest of the engine, hence the term free turbine. And on this type of an engine, I'll get back to this in a second. Well, what the heck? We'll take a peek. Here's a Pratt & Whitney PT6, very popular turbo prop engine. Air comes through a duct on the bottom of the engine and enters the engine. And let's see, there's 1, 2, 3. Looks like 3 or 4 different stages of axial compression, and then there is, and it's hard to see in this diagram, then it has 1 stage of centrifugal compression. Flings the air outward. It has a reverse annular combustion chamber. So we accelerate the gases aft. It makes another turn, and here's the turbine wheel right here. And this turbine wheel drives the compressor. So here is the gas producer, or NG, and then there's a second turbine. The second turbine goes into the reduction gearbox, and that output shaft spins the propeller. So essentially, and then of course the exhaust gases come out and go backwards. So the PT6 is a free turbine in that the turbine that drives the propeller is free to spin separately from the rest of the engine, or you could say separately from the gas producer. Now the nice thing about a free turbine is you can have a prop brake or a rotor brake, and you can run the gas producer part of the engine, and of course the accessory section is hooked up to it, so you can run the electrical generator off of the accessory section, and of course since the engine is spinning and it's got compressors, you can take bleed air off of it and run the air conditioner. So if you've got a big turboprop and you don't have an APU, or you have a big helicopter and you don't have an APU, you can get bleed air for air conditioning on the ground, and you can spin the generator on the ground if you have some kind of a brake, and that way you don't have to worry about a propeller spinning and chopping people up, or a rotor blade spinning and chopping people up, yet you can have electricity and bleed air to run your pneumatics, run your air conditioning. The other nice thing about a free turbine versus a fixed turbine is that you can get away with a smaller starter because you don't have to spin the propeller when you start it up. Therefore, if you have a free turbine, and we'll just say it's a PT6 because that's pretty common. Of course, here's our free turbine. There's a couple more turbines, and the air is going to come underneath the engine and go in the intake. This propeller, since the gas producer is the only part that has to get spun by the starter motor, the propeller actually goes to really, really high pitch. In fact, it actually goes to feather. Oops. The blades actually go to really, really high pitch because we're not having blade latches. We don't have to have latches grabbing the blades at engine shutdown, so the blades actually go to feather. And of course, the other thing on a PT6 is you can see the exhaust duct coming out of the side of the engine. But if it's a free turbine and it's a turboprop, the blade pitch at shutdown is going to be feather because they're not going to waste their time and money on blade latches to hold the blades in place. The reason why it's better for helicopters to have a free turbine is the same reason why you can allow turboprop blades to go to feather, is if we have this output shaft going to, I'll draw it like this. Let's say we had a fixed turbine, and it goes to the main rotor transmission. When we run the starter motor off of the accessory section, that starter is going to have to supply power to the main shaft, and the main shaft to the reduction gearbox, and the reduction gearbox into the transmission, and the transmission into the rotor blades. So the starter would actually having to be run turning the rotor blades, which has a ton of inertia. So we'd have to have a huge, big, giant starter, and it would take up too much weight. So by having a free turbine, you would only have to spin up the gas producer. Then if you had a turbine inside of a shaft driving the output, the reduction gearbox in the output shaft, then it wouldn't have to get spun by the starter. So for helicopters, you almost always see free turbines. If you didn't have a free turbine, if you had a fixed shaft engine, you'd have to put some type of a clutch mechanism here so the engine could spool up and spin up. Like on a piston engine, you got to have a clutch in there so the engine can get started, and then you engage the clutch and the rotor starts to spin, but that's only after the engine gets started. Okay, first we're going to talk about turboprops, then we'll talk a little bit about helicopter control. Propellers on turboprops are very, very similar to that as found on the Seminole, in that you can have low pitch, high pitch, and the blades go to feather, and the way it works is very, very similar. I'll get back to those numbers here shortly. Let's just say you got to understand that in the middle of the blade, this is where it can rotate. it's going to have to rotate around the center of the blade because it's connected to the propeller hub. Now, according to typical aerodynamics of asymmetrical airfoils, the center of pressure is in front of the actual center of where the blade's going to rotate. So as we develop lift, it's actually going to push the blades to higher pitch. That's called aerodynamic twisting force. Aerodynamic twisting force. Okay, that's one of the forces that can work on a blade, work on all blades for that matter. The second one I want to look at is centrifugal twisting force. Centrifugal twisting force. Let's say that you're down here on the ground and you got somebody and they got a string with a rock on it. And they start spinning this string all around and around and around. What's going to end up happening is as it's spinning, this rock is going to come up against the force of gravity and it's going to try to get into the plane of rotation, and that plane of rotation is 90 degrees to the ground. It won't make it all the way up because gravity still has to be overcome, but it's going to get really, really close. Centrifugal twisting force essentially tries to bring all of the mass of the rotating blade into the plane of rotation. If this is the shaft and here's our rotor or our crankshaft, this is a plane of rotation, and we've got this 90-degree angle. Here's our plane of rotation, and we're going to try to bring it into a 90-degree angle. So centrifugal twisting force is going to pull the leading edge into the plane of rotation. It's going to pull the weight of the trailing edge into the plane of rotation, and that's going to try to make it go to a lower pitch. And interestingly enough, centrifugal twisting force acting on the blade is always greater than aerodynamic twisting force. So if you had nothing on the blades, and the blades could change pitch at will as you spun it up and it started creating lift, which of course is blowing the air aft, which we call thrust, the blades are going to go to a lower and lower pitch because centrifugal twisting force is much, much greater than, acting on the blades, is much, much greater than aerodynamic twisting force. Okay. Now, that works out really well. That centrifugal twisting force works out really well. But if we were in, let's see, I'll go to this next one. If we were in a single-engine airplane, let's say we were in or a multi-engine airplane. Now, let's go back. We'll stay in multi-engine airplanes because all turboprop blades act like multi-engine blades. In a multi-engine airplane, here is our airfoil. Here's our propeller, and coming up off at it at a 90-degree angle is a big ol' honkin' counterweight. Now, if we stop worrying about aerodynamic twisting force and all we do is look at centrifugal twisting force on the blades versus centrifugal twisting force on the counterweights, the counterweights are a long way away from the point of rotation. So centrifugal twisting force is going to act on this weight, and since here's the plane of rotation, it's going to tend to pull the counterweights into the plane of rotation and make the blades go to a higher pitch. So on twin-engine airplanes, this works out really good because if everything else quits and the engine is rotating, all the other forces acting on the blades, like you run out of oil so the governor can't pump oil to the engine, then the centrifugal twisting force acting on the counterweights will pull the blade over, bring the blade to a high pitch, and actually bring it all the way to feather, which is almost pointed perfectly straight into the wind. So centrifugal twisting force acting on the counterweights, that takes the blades towards higher pitch. Now, also, in these blades, in these types of propellers, are feathering springs. There's a couple of big giant springs in here, and they're pushing down on a piston. They're pushing down on a piston. This piston, in this picture doesn't show it very well, is connected to the blades. So, whoops, I guess it ought to be connected to the other side of the blade. As this blade gets pushed down, or correction, as this piston gets pushed down, the blades go to a higher pitch. So the second force that's pushing the blades to a higher pitch is the feathering springs. And then if we want to take the blades towards low pitch, then we're going to have to pump oil from the governor. Is going to pump on this side of this piston. And of course, force equals area times pressure, and it's going to push the piston in the opposite direction, and that'll pull the tail of the blade up, and the nose will go down, and we'll go to lower pitch. So governor boosted oil pressure, and it uses engine oil from the engine. It kicks the pressure up to 200 to 300 psi, and that will cause enough force to be able to push that piston up against the feathering springs. It'll exceed the centrifugal twisting force trying to be caused on the counterweights, and this piston will go up, and the blades will go to lower pitch. So, on all multi-engine and all turboprop blades, you got to understand that when somebody first made a turboprop blade, they were making it for a twin engine turboprop, so they wanted to be able to feather it. So if you lost engine oil, then the governor couldn't send any oil to the propeller, so the counterweights and the feathering springs would take over and feather the propeller. If you get on a single engine turboprop, they just use the same propeller as they already had, since they don't have to re-engineer it, and it costs less because they're already making those kinds of propellers. They don't have to redesign it and build it any differently. So if you see a turboprop, it's going to be able to feather the propeller blades and go into reverse pitch, which we'll talk about here shortly, even if it's only a single engine propeller. So effectively, there's two things that take the blade to higher pitch than it is right now, higher from wherever it is, and that's centrifugal twisting force acting on the counterweights, and that's the feathering springs pushing against the pitch actuator. To go to lower pitch, effectively, we're going to say that there's only one thing that does it, and that's governor boosted oil pressure. The engine oil pressure is probably around 100 psi, but that doesn't have enough force to push on that actuator, on that piston. So the governor actually has its own oil pump and kicks the oil pressure up to 200 to 300 psi, so it'll have enough strength to actually push the blades where they need to go. So here's this picture from the side, from normal, and if we put a piston in here and we put our feathering springs in here, now we can look at it. Governor boosted oil pressure of 200 to 350, correction, 200 to 300 psi. It's going to push the piston in one direction towards low pitch, and that's going to pull the blade towards low pitch. The feathering spring and centrifugal twisting force acting on the counterweights are going to make the blades go to higher pitch. And those are the three major forces that move the blades back and forth. Okay, governor operation. The governor is there to do one thing, and that's to keep the engine, this is if you're flying a turboprop, is to keep the engine and the propeller spinning at a certain RPM. If you've got a free turbine, you've got to govern the RPM of the free turbine, as well as you have to take care of the RPM of the gas producer. So you're going to have something on the fuel control to maintain the gas producer RPM. But if you've got a free turbine, you're going to use just like on a Seminole, on any other constant speed propeller driven airplane, you're going to have a governor, and it's there to keep the propeller pitch at whatever it needs so the engine will spin at a constant RPM. So how do you vary that prop pitch? Well, the governor essentially is a mechanical computer. It takes it takes two inputs, and it has three different outputs. The two inputs are what's the prop lever setting that you're telling it. You're actually moving that prop lever and saying, when you push it forward, you're saying you want the RPMs to be higher. When you pull the prop lever back, you're telling the governor, I want the propeller shaft RPMs to be slower. And then it's going to, so that's one input, which is the input from the prop control lever. And then the other input is that it's geared into the engine. Just like on a constant speed prop is on a piston-powered airplane, the same on a turboprop. The governor is geared into the propeller shaft, geared into the gearbox, geared into that free turbine. And if it's a fixed turbine, of course, it's geared into the entire engine. So that if the RPM is lower than, if the engine is lower than what you want, then it's going to reduce pitch so the blade will speed up. Or if the engine's going faster than you asked for, it'll make the blade pitch higher so the propeller will spin slower, so the engine will spin slower. So it can do that. It can either pump oil to, since we need governor boosted oil pressure being pumped out to the pitch actuator. It's a hydraulic actuator, but it's using governor boosted oil pressure instead of hydraulic fluid. If you pump oil to the pitch actuator, the blades will go to lower pitch. If you let oil drain out of the pitch actuator, the centrifugal twisting force on the counterweights and the feathering springs will take the blades towards higher pitch. Or if the engine is spinning the exact same speed that you're asking for, then the governor either doesn't let any oil into the propeller pitch actuator and it doesn't let any out. So sometimes this is called on condition. Whoops. This right here, on condition, or sometimes it's called on speed, in that you've got that prop lever. If we look at the side of the throttle quadrant, and here's the prop control lever, when you push it forward, you're asking for higher RPM is what you're asking for. And so if the engine is spinning slowly, then it's going to need to go to a low pitch, so the governor will pump more oil out to the actuator. Or, when it catches up, we push it up here and ask for a higher RPM, and we're looking at that prop RPM gauge. When the RPM gets up to what you asked for, then the governor will keep that same amount of oil in there, so the propeller pitch will stay at the right pitch to stay at the right RPM. Here's a picture of a propeller with a counterweight. There's a piston inside of here. And if this is a turboprop, there'd be counterweights in there. And you can see the blade is like this, and the counterweight is going at about a 90-degree angle to that, and the counterweight sticks out pretty good. And of course, here's the propeller flange, and that gets bolted to the engine. Here's a cutter view of a Hartzell propeller. You don't have to write down the word Hartzell. But Hartzell makes the vast majority of small turboprop propellers in the United States, and probably in the world for that matter. If it's a Pratt & Whitney PT6, if it's a Honeywell TPE 331, then it's got a Hartzell on it. And you can see there's feathering springs in here. There's a big one, and then there's one inside of it. You can't see it very well, but this is the counterweight poking out mostly at you. And I can't see where the piston, there ought to be some O-rings in there, but I can't make it out in this diagram. But that is a typical Hartzell turboprop propeller, and this piston actually moves in and out on the outside instead of on the inside, like on some propeller pitch actuators. But we can never see it because we're pilots and we don't take the spinner off. Okay. Of course, I already covered the fact that turboprop propellers use variable blade pitch to maintain a constant speed by use of the governor. How far can you go? Well, these are typical blade pitches for high and low. If we look at this being the the plane of rotation. Here's the plane of rotation. If this angle right here is about 17 degrees, that equals normal high pitch. That is, unless you're doing something unusual like feathering the propeller, that's as high a pitch as you're going to get. That's like putting it into fifth gear in a 5-speed car. The faster you go, the higher the gear you need. The faster you go, the higher the pitch you need. So this is going to be typically forever the faster you go. This blade pitch can go down to low pitch, and if this pitch in here is 3 degrees, that's typical low pitch. That's normal low pitch. And that's like being in first gear in your car. So when you're going to be going slow, like on the runway and taxiing, you're going to have a slight positive pitch, and it'll be about 3 degrees. These are generic numbers, but they work pretty good. So in a turboprop, 3 degrees is going to be low pitch under most circumstances. 17 degrees is going to be high pitch under the vast majority of circumstances. 85 degrees is going to be feather. You notice this dotted line right here. Here is the plane of rotation. Here's the propeller. And this angle here is typically 85 degrees. And you're going, well, Mr. Johnson, 85 degrees, that's not 90 degrees. The blade's going to have a little drag. And you have a good point. There is going to be a little bit of drag. However, if you keep the blade pitch slightly higher or slightly less than 90, yes, it's true that when the relative wind hits it, will have a little bit of drag. But if you need to unfeather it, the wind will be hitting it and try to pushing it towards a lower pitch. So it makes it easier to unfeather. And the difference in drag between 85 and 90 degrees of pitch is not enough to worry about. So 85 degrees is full feather. Minus 15, that's full reverse pitch. That's one great thing about turboprops. If it's a turboprop, then that means that you are going to have reverse pitch. Cool reverse pitch. If this is the plane of rotation of the propeller, then right now we have 17 degrees. If we put the propeller right here, it'd be 0 degrees. If we put the propeller at an even lower pitch, say right like this, we could measure this angle in here. And since this is 0, this is going to be minus 15 is the max, typically. The maximum negative pitch. So the propeller blade is still rotating in the same direction. It's just that it's going to be blowing air forward in the reverse direction. Hence the term reverse pitch. And this is one of the really fun things about turboprops, is that you can make the blades go into reverse pitch during landing and slow the airplane down extremely well. In fact, reverse pitch on turboprops works way better than it does on a turbofan. And we'll talk some more about these degrees before this lesson is over. Now, why would you not want to use this in flight? Well, let's say you got that Beech 1900 out there. I know this isn't really a great picture of a Beech 1900, but I never went to art school. So here's our engines, and here's our propellers. And of course you're flying through the air, so the slipstream is going like here. If you put these blades in reverse pitch, then the airflow that was going through and crossing the wings in a normal fashion, that was giving you lift. Now if you try to make the blades go into reverse pitch, then the airflow across the wing right behind the blades is going to be disrupted, and you've lost your lift. over a big chunk of the wings, and it's going to make it really, really easy to fall out of the sky. So all the turboprops I've ever seen have a restriction, and it says do not operate reverse pitch in flight. And the reason is because you lose so much lift that you could stall very, very easily. And it would also affect the airflow across your horizontal stabilizer dramatically. And everybody likes to have full horizontal stabilizer and elevator control. Okay, what are the advantages of propeller prop reverse or reverse pitch? Of course, I already said reduces ground roll. It reduces it dramatically. As soon as you get all three landing gear on the ground, you can go into reverse pitch, and you can go to a really high power setting. In fact, you can go pretty much up to takeoff power as long as you don't exceed the exhaust gas temperature or torque limits, just like you would have on takeoff. And it also increases your ground maneuverability. There's two things here. First of all, if we look at the tires on a turboprop and we want to turn in a really tight turn, we could actually take this inboard propeller and have it have reverse pitch, and this propeller on the outside here have positive pitch, and that would help us turn and put the brakes a little bit here. So it can help us turn. In fact, you could make this turn without using any brakes. So ground maneuverability is one, we can have tighter turns, and two, you got to understand that in a turboprop, if it's doing 50% on the ground at idle, and the blades, if we looked at the blades on the side here, and we had 3 degrees of positive pitch, we're going to be getting quite a bit of thrust off of the propeller on the ground, and we're going to end up having to taxi really fast or use a lot of brakes. So what we're literally going to do is go slightly into reverse pitch. If here is the plane, here's our shaft, and here's the plane of rotation. If we just put that blade right at 0 degrees of pitch, then we're not getting any thrust. If we run it here at 1 or 2 degrees of pitch, we're getting just a little. If we want to slow down, we could make the blades go into reverse pitch or into negative pitch, and we could slow down. So it dramatically helps maneuvering the airplane on the ground. And of course, my personal favorite is it makes that really cool noise. Like when the airplane touches down, they go into reverse pitch and it goes whoa, like that. I really like that noise.
What are the disadvantages of going and using reverse pitch on your propeller blades? Well, since the airflow is interfered with going into the intake, since normally the airflow goes through the propeller blade and then in the intake, instead of helping blow air through the intake, it's actually trying to pull it out. So it does make it a little harder for cooling air to go through the engine, so engine temperatures are a little bit higher than normal. So you need to keep an eye out on the EGT, the exhaust gas temperature, while you're doing reverse pitch. And since the propellers are typically lower to the ground than the intake is, it's not that you're going to throw up rocks when you go into reverse pitch and have them get sucked into the intake and cause foreign object damage to the engine. Much more likely is that you'll throw rocks up and then taxi, and then drive through them and hit the propellers. So it does increase the likelihood of propeller damage. Okay, in turboprops, there are essentially two ways to operate it. You can operate the engine in alpha mode, and you can operate it in beta mode. Alpha mode is probably 95% of the time, and that's the mode you're using in flight. Generally speaking, although a lot of turbine engines idle at about 50% of their rated RPM, turboprops typically have a flight idle. That is, on some turboprops, just before takeoff, you push a separate lever from ground idle to flight idle, and now the engine only comes down to about 80%. Now the blade will go to low pitch, say down to 3 degrees, positive pitch, so you don't get nearly as much thrust, but you're not going to be varying the RPMs very much. As you push the power lever forward, the RPMs will come up to whatever you set it at, and then the blades will go to higher pitch to keep the blades, or rather to keep the engine from going past 100%. Now remember, at 80% engine RPM, you're certainly not producing 80% engine power because there's not a direct and perfect relationship between RPM and power. So as you pull the power lever back and the engine slows down to 80%, you're probably only going to be doing 50 or 60% power. There's essentially two levers if you take a single engine turboprop, like for instance, say a Cessna 208 Caravan. There's going to be one lever sticking up, and that's the throttle, or in jet engines we call it the power lever. Another lever sticking up, and that's going to be the prop lever. And you're going to operate it very similar to you do right now in a piston-powered airplane with a constant speed prop. This lever on the left is fuel, controls the fuel. You're telling the fuel control you want more thrust. And the propeller lever is you're telling the governor that you want to change RPMs. So that's pretty typical. So the vast majority of the time you're in alpha mode, and alpha mode is a little bit of taxi and certainly all the takeoff, roll, climb, cruise, descent, and touchdown. So that's why alpha mode is used the vast majority of the time. You pretty much set the RPMs for redline for takeoff, push the power lever up so you get redline torque. So if we were looking at prop RPM and we looked at the throttle quadrant from the side, the prop lever, you'd push it all the way up so that the prop could hit redline for takeoff. And then you're going to set power using the torque meter. This is prop RPM. Using the torque meter, and if here's redline there, once you set the prop all the way forward so the engine can go to redline, you're going to push the torque lever, you're going to push the power lever up, and long before you get to redline torque, the propeller will have come up to redline, and then it'll just sit there because that's where the governor is going to keep it, and you're going to keep it advancing torque. And the governor, to keep the engine from overspeeding and the propeller from overspeeding, it'll just increase blade pitch. So this is the way you typically do it on a piston engine with a constant speed propeller. Now you can taxi around. Of course, during taxi, the alpha mode is plus 3 to plus 17 degrees of pitch on the blades. So even on the ground, you're going to be generating some thrust. And even if you go to ground idle, like if you're in that Cessna 208 and you've got the power lever and you've got the prop lever, there's another lever sticking out here on the side, and you would pull it back to ground idle after you got down on the ground. Pull it back to ground idle. So if this was RPM, if this is prop RPM and here's redline at 100, normally you'd be between 80 and 100, but if you pulled after you got down on the ground, you pulled the lever back to ground idle, it's going to come down significantly lower. And you're still in alpha mode. That is, when you're in alpha mode, the lever on the left, the power lever, tells the fuel control how much fuel that you want more power, and the prop control tells the governor how fast you want the RPMs. Beta mode is the other operation. Let's have a big one here. Let's say that here is the throttle quadrant, and we're going to look at the power lever, not the prop lever, but the power lever. And we'll just say that right here is flight idle. And that's how far you can pull the lever back in flight. In alpha mode, alpha mode is where you're going to be using the power lever in flight. Somewhere as low as flight idle. During takeoff roll, you'll push it all the way up. Or not push it all the way up, but you'll push it up to redline torque. And the RPMs will be somewhere between 80 and 100%. When you touch down on the ground, there's either going to be some button or some lever, or you may actually have to pull the lever up before you can pull it back, and you're going to actually pull it back into beta mode. Now, the lowest the propeller can get in alpha mode is plus 3 degrees of pitch. Now, during alpha mode, the governor is controlling propeller blade pitch to give you the RPM that you asked for. When you go into beta mode, It's completely different. When you're in beta mode, the position of this power lever, forward or aft, inside, up or down, inside of beta mode, has direct control of the propeller blade pitch. You're literally bypassing the governor. The propeller governor is doing nothing during beta mode. And beta mode goes from +3 all the way down to -15 degrees. So if this is +3, this might be 0. Here's -3. And so maybe here's -10. And you can run your power lever anywhere in here you want to. And you'll notice that beta goes all the way up to +3. So you can actually taxi around in beta with 1 or 2 degrees positive pitch if you want to. Or you can say, you know what, I don't want that. I want to go into alpha mode. You can actually push the power lever. This is the power lever, not the RPM, not the propeller lever. The power lever decides whether or not you go into alpha mode. As soon as you pull that power lever aft and you're in beta mode, now you, with the position of this power lever, you have direct control over blade pitch. And on the fuel control unit, there's another governor that maintains RPM for you. It's not as good a governor as the propeller governor, but it maintains the RPM for you of the engine, so that now you're controlling blade pitch, and if you increase pitch and the engine starts to slow down, it'll put in more fuel. So if you land the plane just as you're touching down, you're right at flight idle, and all the wheels hit, and then you lift up the lever and continue pulling it aft into beta mode, you can keep pulling it as far as you want to. Now, obviously, you're going to want to make sure you don't hit your EGT red line, and you want to make sure that you don't hit your torque red line either. But you can pull the power lever aft into the beta mode and get more and more and more reverse pitch. And if you're watching the prop RPMs, let's just say there's red line, this prop RPM is going to vary a little tiny bit, but it's not going to vary very much. As we go pull the power lever aft farther into beta, closer towards -15, then the load on the engine is going to get greater, and to blow that air back and still maintain RPM, the fuel flow is going to increase. So if we had a fuel flow gauge, and let's just say right here is typically idle, and so here we are at flight idle. If we pull the power lever back, RPMs won't change very much. Fuel flow, however, will go up, EGT will go up, and torque will go up. So you pull the power lever past it, and now the power lever is an oil connection. It essentially is, farther you push the prop lever farther forward, the more oil, or the less oil goes in, and the farther you pull it back, I guess it's the other way around. When you pull it back and you want low pitch, that's more governor boosted oil pressure. So there's more oil that goes to the propeller when you pull it back, and that makes the blades go to lower and lower pitch. Effectively, negative pitch is just a really, really low pitch, because you're actually going from +3 to +2 to +1 to 0, -1, -2, -3, and all the way to -15. Just like feather is really just a very, very high pitch. Negative pitch or is really just a really, really low pitch. And of course, I already got that part right there. Wow, it's like I read this slide 10 minutes ago. And you're going to use beta mode when you're taxiing. And of course, when you touch down, if here's the runway, you're going to come in and touch down. And as soon as you get all 3 wheels on the ground, now you can go into reverse pitch and blow air aft. And of course, you're going to slow down. And then when you turn off the runway on the taxiway, you can either stay in beta mode if you want to, or you can go to alpha mode. You never use beta mode during the takeoff roll, and you never use beta mode in climb, cruise, descent. You're still in alpha mode until you touch down and go into reverse pitch. Now, just like turbojets and turbofans are thrust reverse, if you come into land and you're making calculations before you take off for your landing airport, you're going to base it on yes. You're going to use anti-skid, but no, for calculations purposes, you're going to use no reverse pitch. Now, this is for calculations. In reality, are you going to use reverse pitch? Yes. And all those great reasons are there, like they are for brakes. It reduces your landing roll, and it reduces your brake maintenance so you can keep the airplane up and in service without having to replace brake pads or anything. And it works better than reverse thrust does, so you're going to be able to stop much shorter in a turboprop than you could in a turbofan with thrust reversers. But if for landing calculations, you plan on using anti-skid, you plan on not using the reverse pitch, and if you have to abort the takeoff. So if you have a runway that you're going to take off on, and you're going to calculate your acceleration distance, and then hit V1, your decision speed, just before you would rotate, and then decelerate. This deceleration distance is also based on using anti-skid, but based on not using the reverse pitch for your calculations. If you're going to fly a turboshaft engine other than just an APU, you're going to be flying a helicopter. I've not seen a helicopter that had a fixed turbine. I guess you could. You just have to put a clutch in it. If here's the rotor blades coming down to the main rotor transmission, you'd have to put a clutch. Then you'd have your output shaft and your gear reduction box and your engine. So if you have a free turbine, then you don't have to worry about the engine you don't have to worry about the fact that the starter is going to have to run all of this during engine start. If you have a free turbine, you don't have to have a clutch. You can just let it hook together because the starter is only going to have to run the gas producer. With helicopters, it's extremely important to maintain a constant RPM on the rotor. And in fact, you're going to see that on helicopters, there's actually going to be one gauge, or there'll be maybe several gauges, but it's going to have the rotor RPM and the output shaft, or N2 typically what it is, and they'll probably call it rotor and turbine RPM, and there's going to be two needles on it. If the needles are split, that's not good. What's supposed to happen is the needles are supposed to be right on each other. This will typically be in percent RPM. And there's going to be a very, very, very small range of RPMs in here, maybe only about a 10% spread, where above it is too fast and the parts will be overstressed. And if you go below it, then the blades will start coning. The blades will start coning, and they'll get overstressed and bend, and neither of those are going to be fun things. So with helicopters, you got to maintain a reasonably constant RPM. Interestingly enough, on a helicopter, there's a governor in the fuel control that maintains engine RPM while you lift up on the collective or push the collective down to change rotor pitch. Here is a picture of a simulator, and of course you're going to have a stick for the pilot to fly around. And so the right hand comes in, and this is the cyclic. You don't have to write down cyclic, and that pushes the helicopter forward or aft, kind of up and down, left and right. But then the collective down here, that increases the pitch on all the blades collectively, hence the term collective. And when you lift this up, then all the blades go to higher pitch and the helicopter will climb. The problem is that our rotors, or the RPMs, tend to go down, so you need some system to accurately keep that RPM the same. If it's a piston-powered helicopter, well, actually in a turbine-powered helicopter, this also has the throttle on it, or it controls power. And in turbine-powered helicopters, you set it where you want it, and then the governor on the fuel control keeps the RPMs the same. There we are, and this is kind of like beta mode in a turboprop. Here's another picture of a different collective, and there's some controls on here. And we're going to look at this switch right there. I think I have another picture. Here we go. It says increase and decrease governor RPM. So once you set the power about where you want it, then if you want to increase or decrease RPMs, you just kick it up or kick it down. This is essentially the same as pushing the power lever forward or aft while you're in beta mode to increase or decrease the power. Rotor droop is a term used for low RPMs. Now, the rotor doesn't droop. Interestingly enough, the blades tend to cone up during rotor droop, but this drooping is talking about the RPM, and if the RPMs get too low, that's one of the ways you're going to be really, really unhappy. If you're flying a turboshaft or a turboprop, then it's very common to have what's called a negative torque sensor. And here, we'll try this on a fixed shaft engine, like the TPE 331. Oh boy, that thing has lots of turbines. Woo-hoo-hoo. And normally, the power goes from the engine to the propeller. But if the flame stops burning, say you have a flame out, then you're not going to have power going to the propeller. It's possible that the airflow going through the propeller spins the propeller around, and the horsepower goes back and spins the engine. Inside of the gearbox somewhere is this negative torque sensor. And if the power is from the propeller spinning the engine instead of the engine spinning the propeller, you might get a light telling you, hey, your engine's not working right. It's not producing very much power. You can use this negative torque sensor in addition to having a light come on, is to engage what's called auto feather. Of course, if you've flown a multi-engine airplane and one of the engines quits, then you're going to have asymmetrical drag. So if this engine here quits working, then this engine is going to pull you around to the left, so you have to stick in a bunch of rudder. And you have to decide if this propeller is still rotating, this windmilling, and it's at a low pitch, it's going to cause a lot of drag, which is going to tend to make the yaw even worse. You'll yaw even farther to the right. So you have to feather the blades, point the blades into the wind, so there's not too much drag. And if you have a negative torque sensor set up in the cockpit, you can turn the switch on to arm. And if it's in arm and one of the engines quits producing power, it'll automatically feather the bad engine, hence the term auto feather. So if you're flying a turboprop and you got more than one engine, it's very common to have an auto feather system, and I highly encourage you to use that auto feather system, because if you're at low out, and after you get it past 1 or 2 or 3,000 feet, you turn it off. But it's that first few thousand feet, if the engine quits, you're going to have to decide which engine is the lousy engine and feather it, and you're not going to have much time to do it. So the nice thing is the auto feather system does it essentially immediately and feathers the bad engine, so you get less drag. Also, if you're flying a turboprop or a turboshaft, you could have an auto ignition system, and it's essentially set up so that you hit the arm switch. And again, if the flame goes out in your engine and the negative torque sensor comes on, it'll turn on the ignition switch, and hopefully the fuel will catch on fire, and hopefully it'll only be a second or two where the flame wasn't producing power. The fuel will catch on fire again, the turbines will be extracting energy, and we'll be getting energy to that propeller or that output shaft. I've seen auto ignition systems lots on helicopters, because if you're low to the ground, but low enough, but high enough, if here's the ground and you're up high enough, that if you lost the engine, you'd fall down and not be able to auto-rotate, essentially not be able to glide. You'd be pretty unhappy. So having an auto-ignition system is really nice. So in case it does flame out, the ignition will turn back on, and hopefully, if the fuel is still squirting, it'll catch it on fire, and you'll get power to the rotors again. And it's the same for a turboprop. Over torque is really easy. Over torque means that you went above
the red line torque. If you see the needle coming up before it gets past red line, you need to do something about it. But this is an industry common phrase for turboprops and turboshafts that if an over torque occurred, it means you went past the red line and you're going to have to write it up. And so somebody's going to have to check the engine out and see if any damage occurred. Over temp, also very difficult, is EGT. Here's the red line. You're pushing the power lever up and you're not watching the EGT. You certainly don't want to go past the red line. If you do, it's an over temp. The most likely times for that to occur is at high altitude, high outside temperatures. And if you're in a helicopter and you have to go into a hover, it's also going to be high gross weight, turboprop and turboshaft. Because if you're in an airplane, whether you're at low weights or high weights, and you push the power lever at a high altitude, high temperature, you might actually hit your EGT red line before you hit your red line torque. And that's more likely to occur at a hot and high altitude day. And if you're in a helicopter, as you're trying to pull into a hover, you're also going to be looking at that torque meter. Oops. And as you're coming up on torque, you're also going to want to keep an eye on EGT. And some people might not pay enough attention. You might actually not have gotten up to torque, but high altitude and high temperature at a reasonably high gross weight, you might hit EGT first. If you have questions about turboprop and turboshaft controls, you know how to get a hold of me. If you have any suggestions how to make this lecture better, please let me know. Thank you.